Oh, okay, so I guess we should start. I mean, so it's really pleasure to have.
Oh no.
Benoit is our seminar speaker. So I've been following Benoit, which got me intrigued in quantum wires. And he's really very, very diverse and does many things. So he had early pioneering work on spin liquids and RBB states with Philip Anderson. And he, over the years, his work sort of relates both to deeper questions that are not related to experiments. Like, I mean, they are ultimately, hopefully, like ideas from holography, which originated as I guess all of you know from string theory, applied to condensed matter physics, and assembly temperature dependence of so-called bad metals. But also things that are really directly rooted in the experiment, like for instance, thinking about mesoscopic systems, on-above type cages, or disorder wires, junction arrays, Skyrmion, sort of quantum oscillations. He did a lot of work in fractional quantum Hall effect and graphene. And I mean, many topics. I don't want to go through all of them one by one, but as you can hopefully appreciate, he's very, very broad. And his work is sort of marked by not only its breadth, but also its depth. He tries to really strive for rigorous results, which I really appreciate. And he really tries to understand things deeply, and those things, like for instance, geometrical aspects sort of. So I really very much enjoyed learning about his work in the past and also talking to him. And I'm really looking forward to it. And I should say also, of course, I mean, he's very well known, and he got various prizes, and he got the 2013 CNRS sort of Mother Prize, which is given to individuals that have the highest originality, demonstrate the highest originality and the importance of the work. But I don't want to take too much of Benoit's time, so I'm really eager to looking forward to learning about his work on topological electrostatics. So it's all yours. Yeah, Benoit, you can go. I mean, if you can share your screen.
Okay, well, thank you very much, Zohar, for this very, very warm introduction. I'm very pleased to be with you today. So good afternoon, everybody. And thanks, Andrina, for setting up this virtual seminar. So yes, I would like to share with you my interest for a subject actually that I called topological electrostatics. So, well, this is a subject that mixes very ancient ideas with rather modern ones. And I like this blending of the old and the new. So I'd like to share with you this little adventure. In the end, I will have to tell you a little bit about a few things I've learned in complex geometry. I'm not at all an expert in complex geometry, but I think it's a very cross-disciplinary subject. And I hope that for such diverse audience, you will at least enjoy some of the parts of the talk. And since you have very diverse backgrounds, I decided to really start from the very old. So it's just that my screen seems to be stuck. Okay, so I have to, yes, so what should I do to have the slides moving? Yes, okay. Shall I? My screen seems to be stuck. Okay.
Can you set up now unshare and then share again the screen? Like, I'm not sure.
I have to. Yes. Okay. Let me try to do that. Arrêter le partage. Yes. Okay. So escape. So okay. So if I do this now, okay, I can. Okay. Yes. Does it? Okay. Full screen. Yeah, it seems to. Okay, so
now we can see your.
Now I have to share again. Yes. Okay. Yes, share again. Yes, okay, sorry for the... So the plan of my talk is as follows. I will actually try to give you a sketch of a very brief history of early topological physics, because surprisingly, topology and physics have been very strongly intermingled from the early days of topology. So it's a nice story that I'd like to recall briefly. Then quantum mechanics brought important renewal of topological physics. And I think it's fair to say that one unifying concept that plays a major role is the concept of Berry phase. So I will review this concept, give a few applications of it, and also introduce, for those of you who are not familiar with those objects, the notion of a bundle. Well, it's a fundamental object in topology, in mathematics, but in some sense, Berry phase in systems with families of Hamiltonians, depending on parameters, is a nice setting to get introduced to the notion of a vector bundle. Then I'll mention the quantum Hall effect and one particularly interesting regime where the spin degree of freedom of electrons is somehow strongly entangled with the orbital motion, the quantized orbital motion, and we are going to get the physics of quantum Hall ferromagnets. And later I'll try to outline some of our recent contributions to the understanding of Skyrmion lattices in quantum Hall ferromagnets. So, but early day of topological physics, actually, it started with speculations by William Thomson in around 1869. Well, you know, after the appearance of Mendeleev table, one of the top problems for theoretical physicists was to try to understand what could account for the various forms of chemical elements. Well, it was not clear what was inside atoms, even whether atoms existed, but in case they existed, physicists start to speculate on various possibilities to understand the existence of a finite table of elements like Mendeleev table. And Thomson, who became Lord Kelvin, started to speculate on the idea that there should be a continuous medium with a little bit like a fluid with knots. So those knots actually were directly inspired by the paper by Helmholtz on vortex lines in perfect fluids. So after Helmholtz's contribution, there were interest among physicists in Scotland, and in particular, Tate was an experimentalist, performed experiments on vortex rings in the presence of William Thomson, who began then to speculate on an atomic model based on noted vortices. And then Maxwell, Thomson, and Tate begin to correspond on topological matter. Then, well, Thomson was interested also in vortex lines. Vortex lines, if they are singular, means that away from the vortices, the fluid has no is irrotational. So there was an interest in classifying the flows in these multiply connected regions, which was regarded as the complement of a knot, the knot being the knotted vortex lines. So it was in some sense the birth of the cohomological aspect of topology. Then Maxwell was interested in this book by listing, was one of the first book in on topology, and he gave a review of the book to the London Mathematical Society and incorporated many of those ideas in his treatise on electricity and magnetism. Then, well, stimulated by Thomson's model, putative model for atoms, Tate begins to classify knots with the hope to reproduce the Mendeleev table. Unfortunately, there happened to be a lot more knots, so Tate published huge tables of knots, and later on, mathematicians found that many of the works obtained by physicists turned out to be quite correct. So it was a first period where physics and topology developed very closely in close interaction. Of course, this didn't stop in the 20th century. So in condensed matter, and Zohar has done a lot of work on defects in glass systems and spin systems. So there has been a lot of interest in the subject of defects in solids, solids and liquid crystals. As I'm going to explain in a few words, the key mathematical theory to classify defects is the homotopy aspect of topology, and the topological non-trivial configuration appeared a lot in high energy physics. Well, skyrmions actually were introduced by Skyrm in a model for strong interactions, and there were monopoles and instantons discussed in gauge theories extensively since the 70s, and they were argued by Polyakov to play a crucial role in the mechanism of confinement in QCD. And well, it was also realized that some phase transitions could be induced by topological defects condensations, such as vortices. This is the famous Berezinski-Kosterlitz and Taules transition, which was actually awarded a Nobel Prize in, well, 6 years ago. So that is a very brief history of topologically in physics, but I'm going to specialize now to a condensed matter setting. So as I said, one important subject in condensed matter is a classification of topological defects. And this figure shows what happens in this very simple system, so-called nematic liquid crystals. So you imagine that you have molecules that are described by little rods with no orientation. So they are not spins because they are not oriented. You should remove the arrows from the spins. So if you think in a spin language, such configuration would not be smooth because when you go around the center, the orientation of the rods turns by pi. So if the rods were spins, there would be a line of discontinuity. But since both orientations should be identified, this configuration is perfectly smooth. But you see, if you make a closed path around this defect, it's a closed path in the space of oriented, unoriented lines, which mathematically is the real projective plane. And it's known that such a path in the real projective plane cannot be transformed into a trivial path, into a constant path. This is encoded mathematically by the notion of the fundamental group. The fundamental group classifies the families of closed paths modulo continuous deformations, and for the real projective plane, we have only two classes of path, either the constant path or this topologically non-trivial path. So that's called the 180-degree disclination. For the present talk, the key player is actually, they're called baby skyrmions by high energy physicists, because Skyrm worked in 3+1 space-time dimensions. But for this talk, we are going to be dealing with two-dimensional spatial objects, static objects. So you see here a Skyrmion is simply a spin configurations that so you have a planar system. The spins wind smoothly. There's absolutely no singularity, but imagine that at infinity, the spins are all pointing in the same direction. So now you can regard this infinite plane as, in fact, something that can be compactified, adding one point at infinity, and it becomes a sphere. And now we have a map from the real space sphere to the spin space sphere. And those maps are classified by the second homotopy group, which for the sphere happens to be the group of integers. So in fact, those maps are characterized by a number, which we often call in condensed matter physics the topological charge, and those Skyrmions are configurations that have topological charge 1, and they cannot be undone by any smooth deformation of the spin configuration, provided the spins are aligned at infinity. So you see that, for example, near the center, the spin goes down, and at intermediate distances, you get a vortex configuration. So now our subject actually will have to deal with electrons in a magnetic field at very low temperatures. So it's a very quantum system. And it turns out that in quantum mechanics, there's room for a lot of topological phenomena that are often associated to what is called the Berry phase. So what is the Berry phase? Well, let's take actually the simple example given by Michael Berry already a while ago, nearly 40 years ago. So S is a quantum spin, can be spin half, spin 1, well, it has a fixed value. And N is simply the direction of an external magnetic field that can be applied to this spin. So you have a family of spin Hamiltonians parameterized by N. N lives on a sphere. And so it's a parameter. Now it's straightforward to diagonalize this Hamiltonian for any orientation of N. And we get, if we have a spin 1/2, for example, we have a doublet of eigenspace states that I call psi up of N and psi minus of N. And we get something very interesting is that, well, if we try to look up at the variation of these ground states or excited state as a function of N, there's no way to choose a non-singular phase determination of those wave functions on the whole of the two sphere. So in fact, mathematicians said that this is an example of a non-trivial complex line bundle over the sphere. So the base space is the parameter space with N the parameter, so the spin, the orientation of the applied magnetic field, and the fiber over N is the complex line generated by either the ground state, psi plus, or the excited state, psi minus. So in this case, the fiber has dimension 1 over C. Dimension 1 is a complex line. So we are talking of a line bundle. And note that unlike the wave functions, the projectors are smooth everywhere on S2. So actually, if you insist of choosing a choice of phase, of choosing phases psi of n for every n, you're going to get some singularities, but the map n to psi of n is what is called in mathematics a section of this line bundle. And try to remember this definition of what we call section, because it's going to play a role later on. Now, this psi of n depends on the position. So if we compare how psi's differ at nearby values of the parameters, we get the so-called Berry connection. It's like a vector potential on the sphere. And as usual, you can transform, for example, a contour integral of this vector potential by area integral, giving the Berry curvature. And there's something quite remarkable for this simple problem, is that if you have any contour gamma, the integral of this Berry connection is nothing but the solid angle across this contour times the value of the spin, which can be 1/2, 1, 2, or 5/2, and so on. So the Berry curvature is basically given by the magnetic field of a kind of magnetic monopole that would be located at the center of the sphere. And in mathematics, it turns out that, well, the integral of this Berry curvature cannot take arbitrary values. In this situation, it's an integer, which is called the Chern number, which happens to be twice, actually plus or minus twice the value of the spin. Spin can be half integer or integer, so the Chern number is always an integer. So the line bundles actually on the sphere are classified by their Chern number. And we're going to make extensive use of those notions later on. So that's why I'm also using the Berry phase as a sort of pedagogical example to introduce the Chern number. So actually, one interesting application of those ideas of Berry phase, and that's a subject I worked on many years ago, but imagine that you have a system of electrons which have some spins that make a sort of twisted spin configuration. And imagine that you have a mobile hole that can move inside such a background. So you can make a little movie. What happens if the hole hops from this side to the next side? Well, there will be a spin moving backwards. And if you keep doing this along a closed loop, you see that the hole went back to its original position, but the background, the spin background, has been updated from the dashed blue to the red configuration. So a question of interest is how could we compare the two wave functions before this experiment and at the end of the movie? So just to put this in a more mathematical term, we have an initial wave function, which is a product of spin wave functions that I denote Chi1, Chi2, Chi(n minus 1, where 1 to n are just the sites along this loop. And then at the end, you have a cyclic permutation of those spins. Now, when you consider the overlap between the initial and final configuration, in the limit of a smooth spin background, it can be shown that this overlap goes to 1 in modulus, but it has a phase which is given by simply the contour integral of the Berry connection, that is the solid angle spanned by the spins on along the path times the spin. So it shows actually this is exactly the same result that you would get if you forget about the spin, but if you have a hole moving in external magnetic field, because in some sense, the effect, that's exactly the content of the famous Aharonov-Bohm effect. The effect of external magnetic field can be expressed through this global phase. That's especially clear if you use the Feynman approach to quantum mechanics. So in some sense, this relation shows that the presence of a twisted backgrounds can mimic the presence of some fictitious electromagnetic field. And in fact, this has been used in experiments. That's one of the ways to generate artificial gauge fields in cold atom systems. So one other very important application of the Berry phase is for electrons in periodic potentials. So the parameter here is the momentum K. You have energy bands, and K belongs to the Brillouin zone, which has the same topology as a torus. So each band actually carries a complex line bundle over the Brillouin zone. And there's, again, for this bundle of periodic wave functions, Bloch wave functions, there's a notion of parallel transport and Berry curvature. And this Berry curvature is really observable. It was found by various people, started in the 50s, but it was revisited and generalized in the 90s, in particular by New and co-workers. There is this additional term, so-called anomalous velocity, which is a sort of, you see the analogy with the Lorentz force due to a magnetic field. So the magnetic field is in real space. The Berry curvature of a band structure is, if you wish, like a magnetic field, but in K space, and it generates an anomalous velocity. This anomalous velocity actually has been observed in all kinds of experiments, but some direct visualization of it could be achieved in a cold atomic system. So when you drive the system of cold atoms on optical lattice with an external force, there's an anomalous velocity that appears that is perpendicular to the external force. So that's the, yeah, of course, this has had many applications in all kinds of materials. So now I would like to turn to the subject of quantum Hall ferromagnets. So first, briefly, the quantum Hall effect is, well, one of the most spectacular effects in condensed matter physics. So that's taken from one of the early experimental results in the mid-80s. So this is the magnetic field. The very wiggly curve is the longitudinal resistance. So you see a sequence of almost states where the resistivity vanishes, where it's finite, and the zeros of the longitudinal resistivity correspond to plateaus of the transverse resistance, the whole resistance. And what is remarkable is that those plateaus appear at always the same values of the Hall resistance measured in fundamental units of the Planck constants divided by the square of electron charge. So this striking result, okay, there are many aspects to the theory, but very briefly, at least for the so-called integer plateau, 1, 2, 3, 4. So I'm going to give you the meaning of these numbers. This is simply the so-called filling factor. So each quantum state actually occupies, well, if you have electrons in a uniform magnetic field, the single particle spectrum is quantized in what is called Landau levels. So Landau levels are the result of, well, classically you have cyclotron orbits and particles. Well, the remarkable feature of the cyclotron orbits is that the frequency is independent of the size of the orbit. And this is also a common feature with the harmonic oscillator. So this common feature leads to the fact that the spectrum has always these regular spacings. The energy difference between two levels is simply h bar times the cyclotron frequency. But now these cyclotron orbits can be anywhere in the plane, so these Landau levels are massively degenerate. And in fact, the degeneracy can be understood rather intuitively by seeing that each quantum state occupies the same area as a flux quantum. In other words, to know how many states you have in a Landau level, you simply compute the flux, magnetic flux across your system, 2D system, and divide it by the flux quantum h over E. And the so-called filling factor is the number of occupied Landau level. So you see, when it's an integer, all excitations are gapped, because the only thing you can do is to empty an occupied state in one of those occupied Landau levels and promote it to the unoccupied one, which costs finite energy. But for the fractional fillings, the kinetic energy operator is highly degenerate. So that accounts, at least for the existence of the integer plateaus. Well, of course, for the so-called fractional plateaus, you need, of course, to introduce Coulomb interactions, because here the spectrum is gapless if you have only the kinetic energy. But okay, we are going to deal mostly with the integer effect. And the most remarkable result maybe that was obtained in the early 80s was to relate actually the whole conductance to the total Chern number of the occupied bands in the system. So if on top of that you add a periodic potential, you're going to get energy bands, and each band, as I said, has a Chern number, and the whole conductivity is total Chern number of the occupied bands. That's a famous result by Taules, Komoto, Nightingale, Delnois, and this was also generalized by a mathematician Avram, Seiler, and Simon later. And the figure actually represents the famous Hofstadter spectrum. So horizontally, this is the energy. Vertically, you have the flux per unit cell. So you have a periodic potential on a square lattice. You have a gapped spectrum, and the color codes represent the values of the Chern numbers in the gaps of this Hofstadter spectrum. So that was one of the first appearance of Chern numbers. I mean, in physics, because they were directly related to an observable quantity. which is the whole conductivity. Now, there has been interest recently in systems that have several, on top of the orbital motions and the electron spins, we can add additional degrees of freedom. Well, we often, by analogy with particle physics, talk about flavor. So there are systems where you can have two layers, two electron gases, so bilayer system. And you have also the graphene system, which is very, very intriguing because you have an hexagonal lattice. So you have a unit cell composed of two atoms, well, say one dark and one white. And these two sublattices give rise to twofold internal degree of freedom, and that plays the role of some kind of isospin. And some time ago, we found with Roderick Messner and Mark Gerbig that there's a nearly SU4 symmetry of the Coulomb interaction in this spin and isospin degrees of freedom. So in fact, the setting that we are going to work with is that we are going to imagine that we have electrons in a strong magnetic field, that we have these internal degrees of freedom, spin and isospins, and that will be in a regime, maybe not too low temperature, where we have a SUN symmetry, where n is the number of internal states. So that's so to summarize, we have n internal states, an integer filling factor m. So m can be 1 to n-1, because we are going to assume that only the lowest Landau level is occupied. So, I mean, for the orbital motion, we imagine that only the lowest Landau level is occupied. So we can fill up to m fermions, to n fermions, sorry, per orbital state in this Landau level. So the filling factor can be at most n, and the integers are 1, 2 to n-1. So we are going to be interested in these integer filling factors. So actually, there are systems where the direct Zeeman interaction with the external magnetic field is not the leading interaction in the case of a small G factor, but the leading interaction is the Coulomb interaction. And in fact, if you have a highly degenerate Landau level with Coulomb interaction, it's known in atomic physics that you get a ferromagnetic state. The reason is simple, is that if the spins are parallel, you lower the energy of the system by putting all the electrons in a totally antisymmetric wave function that creates a node when two electrons want to be at the same place in space. So we have a ferromagnetic state for those integer filling factors. The main question is what happens when the filling factor deviates a little bit from an integer. So you could say maybe we are going to create some localized holes, and the background will remain ferromagnetic. That's the most natural expectation. And what's remarkable in such system is that there's this very counterintuitive phenomenon, is that the ferromagnetic state is replaced by slowly varying textures, in fact, that form Skyrmion lattices. So that's something that was predicted already a long time ago, in the 90s, and there have been only indirect observations, because for 2D electron systems, it's kind of difficult to visualize the spin configurations, but there have been, for example, evidence that Skyrmion crystal form, for example, when they melt, there's a peak in the specific heat. When they form, the collective modes of the spin texture provide an increase in the nuclear magnetic relaxation. Well, and there were various spectroscopical experiments. So we have some good reasons to believe that such Skyrmion crystal can be formed. But it's, of course, very useful to be able to do numerics. So I'm flashing some numerical results due to a group in Quebec, in Sherbrooke, where they've done extensive Hartree-Fock calculations for a 2D electron system in the presence of a magnetic field and various, so that's for the bilayer system. And there are some in the regime where anisotropies are weak, that is a spin and layer degrees of freedom form almost a SU4 symmetric system. We get what I like to call entangled textures. So that this corresponds to n equals 4 and m equals 1 when field Landau level. So if you take a snapshot of the system wave function, you could see that on one layer, you have a beautiful Skyrmion crystal, but on the other layer, you get the Skyrmion crystal shifted by half period. So you get a sort of massive entanglement between the spin and degrees of freedom and the layer degree of freedom. So that's this entanglement between spin and layer that I found quite fascinating when I started to be interested in this system. And actually, I would like to show you that this subject now is moving ahead also due to spectacular experiments. These are experiments that were published 2 years ago. So this is on a graphene sheet. Well, these experiments actually, by tuning the filling factor locally using various metallic gates, it's possible to have a situation where in green you have 2 field Landau levels, here 1 Landau level, and in between it can vary. And on the left, you have the possibility to inject spin waves, because here in pink, it's at nu equals 1, it's supposed to be totally polarized. So you have a ferromagnetic system on top of which you can get small ripples, so the so-called magnons. And the question is whether magnons can propagate from this injector on the left to a detector on the right. And depending on the filling factor, for example, at nu equals 1 in the middle, magnons propagate very well. So that's the cartoon to account for the situation when the filling factor is 1. So we have a perfectly ferromagnetic system. But when you deviate from this filling factor nu equals 1, the transmission of magnons becomes very poor. So it's an indication that the spin structure in between is very totally reorganized when you change the electron density or the filling factor by a tiny amount away from nu equals 1. So, and I have the impression that we are just at the beginning of a new series of experiments that are going to probe in great detail the dynamics of these generalized spin configurations. So that's the motivation. Now I'd like to do a little bit of theory in the remaining time. So what is the, okay, I'm a theorist, so I'm trying to work with simple models. So the model will be based on a combination of Hartree-Fock and the Landau theory of phase transition. So in other words, in the spirit of Landau, we have to understand what is a good order parameter to describe, for example, the structure of those Skyrmion lattices. But since the Skyrmion lattices are in homogeneous states, we have to understand first the order parameter of ordered states. And that's where we need a little bit of mathematics, because when you have a filling factor m, basically, you imagine that for each orbital level, in the lowest Landau level, you have to choose m occupied states for m electrons among n possible states. And if you're doing it in a mean field way, you're going to use a Slater determinant. And what you need to know is basically which states are occupied. But choosing m occupied states means choosing actually an m-dimensional subspace of space of dimension n. So therefore, the manifold of ferromagnetic states, actually, when the filling factor is m, is the complex manifold of the formed by choosing all possible m-dimensional subspace in C to the n. And this family of m-dimensional subspace form what is called the Grassmannian manifold. And a very interesting special case is when m equals 1, we get a collection of lines. This is nothing but the complex projective space that is also probably more familiar. So we have this order parameter that lives in this Grassmannian manifold. And now suppose that we have a smooth Skyrmion lattice. We are going to get a smooth map from our physical space manifold to the Grassmannian. And in fact, in practice, a Grassmannian, okay, I was maybe a bit fast, to describe an m-dimensional subspace in an n-dimensional space, we can choose m basis vector, and we could view those m basis vectors as the m columns of an n times m matrix V. So to represent a map to the Grassmannian, we get a collection of maps, and there will be two types of symmetries in this problem. There will be a global symmetry, because I said that we are working in the limit where all internal states are physically equivalent. So we have this global SUN symmetry. And when Skyrmion crystals form, this symmetry is spontaneously broken, giving rise to Goldstone modes besides the usual phonon modes. And these are the additional Goldstone modes that are seen, for example, in experiments like nuclear relaxation. But we have also a local gauge symmetry, because if you have an m-dimensional subspace of C to the n, you have infinitely many ways to choose a basis in such subspace, and making different basis changes in this V matrix description amounts to multiplying to the right the V matrix by an SUM matrix, which is allowed to vary from one point to another. So it's really an example of a local gauge symmetry. So now this is in substance a classical description. Quantum mechanically, we have to transform this into a Slater determinant projected onto the lowest Landau level. I'm not going to detail the mathematical tools to do this, but the main outcome of this is something very, very interesting, is that now I told you that you start with a system that has a filling factor close to M. So M, well, L is what is known as the magnetic length. That's the flux density. 1 over L squared is the flux density in the system. So you expect that when the field is homogeneous, filling factor M, the electronic density should be a constant. But because of this projection to the lowest Landau level, it turns out that there is an extra term, which is nothing but the topological charge density in the spin background. And if we integrate the topological charge density over all space, we get the number of Skyrmions, or the total topological charge. So that's the local version, that's the integrated version. But you see that when the filling factor is not exactly an integer m, the electronic number is fixed by electrostatic reasons, it means that you have to have a non-zero total number of Skyrmions. So that provides a constraint for your system. So actually, maybe you may find that this is not very intuitive, why the system wants to twist the spins when you're no longer at an integer filling factor. So actually, you may remember what I said about the motion of holes in a twisted magnetic background. In some sense, when the spin twists, this generates an effective magnetic field due to the Berry phase of the spins. And in fact, this can be recast by saying that if you consider now this effective magnetic field, that is the sum of the external one and the one generated by the spin texture, you get again an integer filling factor m. So this is an alternative way to understand the fact that when you deviate from integer filling factor, a spin texture wants to form. Now, the problem I was interested in was to understand better what kind of spin configurations you get in such system. For this, you have to minimize an energy functional in the presence of this constraint on the topological charge. So when there's a finite number of Skyrmions, you know that the ferromagnetic state cannot be the ground state of the system. Spins have to twist, it's mandatory. But how do they twist? The total energy turns out to be the sum of exchange energy. So it's a la Landau, it would be a sort of grad square of the magnetization density. But the fascinating effect is due to what we call the non-local term in the energy potential. And in fact, if we look at this equation, we see that each time you create a twist in the spin background, you do two things happen that are linked. You create some topological charge density or Skyrmion density that translates into a modulation of the electronic density. So in fact, in other words, those Skyrmions that appear are charged objects. Each Skyrmion somehow binds the good old electronic charge. That's why I call this subject topological electrostatics. And so, in other words, when you have a non-trivial topological charge density background, you get simply the Coulomb interaction due to the charges bound to those Skyrmions. So that's non-local if you start with the usual long-range Coulomb potential. So in summary, suppose that you fix the filling factor slightly away from an integer m, you fix the total number of Skyrmions, and to find the optimal textures, we have to minimize the total energy. But if the number of textures is small, the non-local term is going to be small. So I have the impression that it's a very reasonable way to proceed in 2 steps. First, minimize the local term in the presence of this topological charge constraint. And actually, it turns out that when you do that, it was known in high energy physics in the 70s already. This leads to a continuous family of degenerate configurations described by holomorphic maps from your physical space to the Grassmannian manifold. So that's where the complex geometry appears. We have somehow to be able to describe the phase space, that is the space of such maps. And as I said before, it's a sort of baby problem for in the presence of non-abelian gauge symmetry. That was one of the reasons why I was so interested in this problem. And then, so all those holomorphic maps minimize the local energy, the local exchange energy. Now, among all of them, we are going to try to find those which minimize the non-local term among those dot-generate configurations for the local functional. And actually, the non-local, as I said, is nothing but electrostatics produced by topological charge background. So as usual in electrostatics, if you have a continuous fluid of electricity, since the all elements of the fluids repel each other, you minimize the energy when you keep a uniform density for your fluid. But here, the problem is the density is not an arbitrary function of space. Q of R comes from a topological charge density. I didn't give you the formula, but Q of R cannot be an arbitrary function of R. That's what makes the problem interesting, and sometimes with counterintuitive features. So I guess it's almost close to the end. So I'm okay. There were several types of questions that we've been interested in. So I said, okay, how to construct and parameterize the whole family of holomorphic maps from the physical space to the Grassmannian manifold. And actually, it's an important problem in mathematics. And here, I don't have much to add to what is known by mathematicians, but we were interested to minimize the spatial variations of the topological charge density, having in mind this Coulomb energy problem that I've just outlined. And I would like to maybe finish by giving one idea, one flavor of the result. I had a lot more to say, but I want to keep a reasonable time. So let's work actually on the sphere. So we are going to our physical space. We are going to compactify it into a sphere, back to the Wikipedia picture of a Skyrmion that I've shown before. So we are going to use a stereographic projection to map the plane, physical plane, onto a sphere, and coordinates on the plane, or x and y, that are lumped into z, as usual, x plus iy. Now, suppose I want to do the following. I look at maps, holomorphic maps from the sphere. We are not going to take the most general Grassmannian manifold. We are going to assume that the filling factor is just 1. So in fact, at every point, you choose a line in C to the n. So the target space is the complex projective space. So it can be shown that holomorphic maps are just collections of polynomials n polynomials. So you have a map from Z to C to Dn, and with entries P1, P2, Pn. And the topological charge is simply, turns out, the degree of those polynomials. Well, that's the formula for the topological charge density. And you can write up very simply a condition for the charge topological charge density to be constant. And if you massage it a little bit, you find actually that I'm not going to take now too much time to give you the details, but there's a sort of very interesting phase diagram, which is as follows. For this funny electrostatic problem, you have two important parameters. You have the number of internal states n, and you have the number of skyrmions d on the sphere. And in fact, we found that there's a phenomenon that is quite remarkable, is that there's a sort of phase, I mean, two phases. Well, in this case, there is a unique solution up to global SUN transformation, giving a uniform topological charge density. And this is remarkable because then it means that those textures, they are optimal for any repulsive potential. If you manage to produce a uniform topological charge density, the associated electronic density will be uniform, and you will clearly minimize the electrostatic energy. If, on the other hand, you increase the number of skyrmions, and as I said, is the number of internal states, so it's 2 or 4 for graphene, or I mean, it's given by your implementation, physical implementation. But if you increase the number of skyrmions, you reach a regime where no uniform solution exists. So indeed, there exists a kind of fuzzy charge crystal. And one of our surprises is that, okay, that was what we found in the example of the sphere, but there's in some sense, almost the same occurs for a torus. So a torus is a convenient way to describe a crystal, skyrmion crystal on the plane, because if you have a unit cell, you can visualize it as an elementary torus. And we get this same time of phenomena, and we also managed to generalize this type of picture when you increase the filling factor m, not just 1. So we have to work with the maps to Grassmannian. So we need a little bit of mathematics with vector bundles. On the sphere, we get some exotic phenomena where you get these numbers describe some deformation modes, which are not Goldstone modes, and for these optimal textures. And it's still a challenge for us to try to understand what these deformation mean physically. And on a torus with m equals 2, it's more the generic situation again, with a sharp transition between the regime with uniform charge density and the regime of the fuzzy crystal. So I think I will end here my presentation. Well, for me, indeed, in the course of this study, I noticed what is clear actually to any physicist is that there's a deep difference between m equals 1 and m equals 2. And well, actually, mathematically, it's related to the fact here that you have an abelian gauge theory, and here a non-abelian one. And so it's much more complicated to identify the associated phase space. And that's where this ideas about vector bundles are useful. Also, well, there are probably interesting connection with mathematics, because we found that on the torus, to realize this uniform topological charge configuration, you have to use special vector bundles which don't have any automorphisms, or, well, that's the mathematical name for gauge transformations. And this seems to be related to concepts that have been used by mathematicians in all kinds of subjects, in particular the subject of stability, which plays a crucial role in many situations. The existence of Hermitian Einstein matrix, or the construction of moduli spaces of vector bundles. And I would like also to point out that this funny electrostatic problem of trying to get a uniform topological charge density from a texture has been also applied in other areas of physics, the subject of Chern band insulators, for example, trying to produce quantum Hall physics without a magnetic field, but just playing with the band structure. So it's possible to generate what is called a topological band structure. And it turns out that when the Berry curvature in a band with non-trivial topology is nearly flat, it realizes some close analogs of the quantum Hall effect, which requires a large magnetic field. So it has stirred a lot of interest in quantum metaphysics. And as I said, you have the generation of artificial gauge fields in cold atom systems, and also the subject of quantum pumps. So to close, I was surprised by how this subject took us from various aspects of physics and mathematics. And okay, I hope that I didn't lose you too much, because I realized that I discussed many subjects, but for me, that's one of the things I like about physics, is that it's whatever we do, it's bound to be connected to many other subjects. So, okay, I hope I could share this at least with you. Thank you very much.
Yeah, thank you very much. It was a fantastic talk. Actually, I don't see the audience, so so maybe if somebody has questions or actually, but I mean, is there? I mean, this fuzzy sort of phase. I mean, is it sort of? Is there an easy way to understand it? I mean, what does it really look like in more detail?
Yeah. Okay. So maybe I should have produced some pictures, but I think that, well, you know, a Skyrmion crystal, I may have a picture like this, but you get, for example, these Skyrmions here, and you get the topological charge density profile, but what I should say actually is the following, is that on the sphere, you get something really remarkable, is that in this phase, the topological charge density is totally uniform. I mean, really, that's quite impressive. In other words, the ground state doesn't depend on the exact form of the potential. Actually, the way we discovered this was totally empirical. My friend and colleague Dimakov-Regine minimized the total energy using different shapes of the potential, you know, 1 over r, log of r, or delta function of r, and he always found the same results, which looked a bit intriguing to us. And in fact, we were just sitting on this line n equals d, where it's possible indeed to have achieve a flat profile for the topological charge density. And in other words, for a given number of Skyrmion, if you have enough components of your internal space, you can always manage to find a completely uniform topological phase density. But in this case, the fuzzy crystal, well, here in some sense it's harder to describe. It's more, I would say, conventional in the sense that you get a crystal, so you have spots where you have a accumulation of plus charge, and then spots where you have a minus charge above some average charge. But the shape of the crystal depends actually on the precise potential that you take. So in some sense, the real surprise to us was this lower corner of this phase diagram, because in some sense we expected to find crystals, but this phase is so okay. Maybe phase transition is a bit misleading. I don't think you go discontinuously from here to here, but here you have a minimization problem whose minimum is almost independent of the potential that you take, and on that side it depends on the energy potential function that you take. So that's really the surprising result. Yes.
Very interesting.
Thank you so much, Benoit. I think, are there any other questions? Because otherwise I think we need to wrap up, because we're
sure. Yeah.
Hour, I think.
It was a bit long, but sorry.
It was great. Thank you so much for the talk.
Thanks a lot. Thanks, Andrina. So thanks.
Yeah, thank you so much for making the time, and thank you so much for joining us so late for you.
Thank you very much. Thanks a lot. And, hopefully once I'll be able to meet you live.
That would be fantastic. Thanks a lot.
You're welcome. Thanks a lot, Andrina. And I hope to see you soon, so either side of the channel.
Yeah, absolutely. And I'm sorry that we started a bit late also. I'm sorry about that.
Okay.
But this is a really interesting